All right, let's dive right into this explainer, where we're going to demystify a highly dense, incredibly abstract mathematical concept, the Weil-Moore Anima from Dustin Clausen's 2026 paper. We're going to approach the creation of this topological space as the ultimate esoteric culinary process. Think of it like brewing the perfect, most mathematically pure soup imaginable. But beyond the metaphor, we really need to understand why this matters. Clausen's work is a fundamental breakthrough because it solves a critical problem in algebraic topology and number theory: how to capture the absolute, invariant essence of a space without losing information to arbitrary topological constraints. Here's the menu for today's explainer. First, escaping the point-set world, then extracting the mathematical soul, brewing condensed mathematics, following the Poitou-Tate recipe, the Weil-Moore synthesis, and finally, some number-theoretic flavors. So, let's start with part 1, escaping the point-set world, or getting our raw ingredients. You know, in the status quo of classical point-set topology, sets are pretty rigid. The points are completely stuck exactly where they are. They're essentially acting as our chunky, static raw materials. But for what we're cooking up today, we need a fundamental shift in texture. We need the homotopic flexibility of an anima. Actually, think of an anima as an infinite groupoid. In this fluid structure, a point isn't trapped anymore. Instead, it's free to move around and naturally animate within its connected component. We're no longer just looking at isolated dots. We're looking at spaces where points are connected by paths, those paths are connected by higher-order paths, and so on, infinitely. This homotopic freedom is the absolutely crucial foundation for everything we're about to build. Moving right along to part 2, extracting the mathematical soul, which is basically our straining process. I absolutely love this quote from Alexander Bielenson. He says an anima is something like a soul, what remains of the CW complex when it is stripped of its worldly point-set incarnation. It instantly humanizes this massive abstraction, right? Think about it. When we construct a topological space like a CW complex, we're forced to make all these arbitrary choices just to glue the point-set topology together. Passing to the anima acts like a fine mathematical strainer. It actively discards all those arbitrary, rigid choices and leaves behind only the pure, invariant homotopy type. We are literally straining out the physical constraints to extract the true, unadulterated soul of the space, and that becomes the refined broth of our entire dish.
Which brings us to part 3, brewing condensed mathematics and setting our constraints.
Now, we can't just let this complex topological broth boil over into total chaos. We need strict constraints, our precise temperature control, if you will. Enter the Moore anima. This is a condensed anima over a locally compact Hausdorff group. Crucially, it demands that all higher homotopy groups, from degree 2 upwards, are themselves compact Hausdorff. But here's the absolute key to this stage of the recipe. The higher R mod Z cohomology automatically vanishes. Why does that matter? Well, in condensed math, a locally compact Hausdorff base interacting with vanishing higher cohomology creates a perfectly stable environment. It's the exact chemical reaction that guarantees our topological space won't unravel when we start adding more complex dimensions to it later on.
Okay, part 4, the Poitou-Tate recipe. It's time to simmer the soup.
This is where the heavy mathematical machinery really goes to work using obstruction theory. We're simmering this space, building it up layer by layer through a Poitou-Tate. Step 1, we start with our stable end-stage Moore anima base. Step 2 requires us to identify the exact homotopy group we need to add to reach the next stage, which is canonically dictated by the H to the n+2 R mod Z cohomology group. But step 3 is where the real magic happens. Normally, adding a layer introduces null homotopy obstructions, right? Like mathematical roadblocks that prevent the space from forming. But because we strictly enforce those Moore anima axioms earlier, the vanishing R mod Z cohomology acts as an automatic mathematical sieve. It inherently clears those null homotopy obstructions right out of the way. So because the obstructions vanish, we're mathematically cleared to continuously layer higher homotopy groups one by one, simmering the anima to absolute perfection.
Let's move to part 5, the Weil-Moore synthesis, where we get our perfect broth. To reach this ultimate Weil-Moore state, we have to perfectly align an untruncated, refined class formation with those rigorous Moore anima axioms. It starts with a refined class formation of Z-type, R-type, or compact type. But the real bonding agent here, the ingredient that perfectly emulsifies the whole broth, is an isomorphism mapping directly to the associated Weil groupoid. By mapping its first truncation directly to the Weil groupoid, we lock the fundamental algebraic structure firmly in place. Combine that precise formation with the Moore vanishing cohomology axioms we established earlier, and boom, the synthesis is officially complete. We've successfully built the Weil-Moore Anima.
Now we've just navigated some incredibly heavy machinery. Infinity groupoids, infinite Postnikov towers, vanishing cohomology, the whole shebang. So stepping back to look at this monumental construction, you really have to ask yourself, why go through all this trouble just to build this specific anima?
The answer is absolutely beautiful. It's because the Weil-Moore Anima canonically recovers the underlying refined class formation via untruncated cohomology. This is literally the holy grail for this kind of topological recipe. Usually, when analyzing these profound structures, mathematicians are forced to use truncated cohomology, basically chopping off infinite layers of data just to make the math workable. But by building the Weil-Moore Anima, we avoid that compromise entirely. We stripped away the worldly point set shell, boiled it down to its topological soul, and yet we can cleanly pull the complete infinite truth of the space right back out. We lose absolutely zero information, capturing the purest essence of the space in a fully untruncated form. It's just incredible.
And finally, Part 6, Number-Theoretic Flavors. Let's serve this soup.
When we applied this beautiful construction to the real world of number theory, specifically looking at the Weil-Moore analogs of Tate's classical theorems in Galois cohomology, a profound structural order emerges around the number 2. We discover that these newly synthesized animas possess a strict cohomological dimension of exactly 2 when working with discrete coefficients. And look, this isn't just a neat piece of trivia, it's a massive structural revelation. Having a strict cohomological dimension of 2 perfectly aligns the abstract topological behavior of the Weil-Moore Anima with the fundamental properties of local fields and function fields. It gives mathematicians a unified, beautifully ordered way to understand these profound Galois symmetries that were previously just so much harder to cleanly extract.
So, having successfully brewed the Weil-Moore Anima, it leaves us with a pretty lingering, provocative thought. If we can take something as rigid as a class formation, strain out its worldly point set constraints, and animate its true invariant topological soul, well, what other rigid mathematical ingredients are out there, just waiting to be boiled down and animated? Thank you so much for joining me on this explainer, and keep questioning the foundations of the math around you.